like to thank the organizers for inviting me. What I'm going to talk about is some new and perplexing things we are learning about or trying to learn about in interstellar chemistry. And these involve reactions involving electrons. So it is, I think, appropriate for this meeting. Now, I wanted to first show you something we do understand, because there'll be a lot we don't. And what we do understand are the clouds that you're looking at, these dense, cold objects. They look like black dust lanes here, which is what they are. These are called cold, dark clouds. They're common. And you can't study them in the visible because of the dust particles that extinguish visible and ultraviolet radiation. They are studied at longer wavelengths. For the gas phase molecules, mostly in the millimeter wave. It's a rotational spectroscopy. And one learns, among other things, that these objects, despite their looks, are not really homogeneous. They're quite inhomogeneous, and the denser portions, which are called cold cores, often are starting a collapse to form low-mass stars. It's very interesting to astronomers as well as chemists and physicists. Anyway, the chemistry is observed to be rather exotic. If you consider that the Earth is not exotic, what's there is exotic. And very unusual molecules. Interstellar clouds are weak plasmas, and there are positive and negative molecular ions. There are all sorts of unsaturated organic molecules. There are very unusual isomers, radicals, three-membered rings. Anyway, a large number of unusual molecules that many chemists wouldn't even believe. And for many years, we've understood this at least semi-quantitatively in terms of ion molecule chemistry, in which the ions, mostly positive ones, that are produced by cosmic ray bombardment, and then undergo ion molecule and dissociative recombination reactions. And there are also some other neutral reactions. All of these reactions, of course, since they're occurring in a source with 10 Kelvin, can't be endothermic and can't have any barriers. So that's why the ions do dominate the chemistry. Okay. And the density, something like 10,000, is the highest density seen. All right, now what I'm going to talk about are some of the two of the three topics, anyway, involve observations with something called the Herschel Telescope, the European Space Agency telescope, with this detector actually supplied by NASA, and it looks at the heavens in the far infrared, which is impossible from the ground, even in the best desert sites, because of water vapor in the atmosphere. So what we're seeing then for the first time with this telescope is the far infrared spectra, and it includes both high-frequency rotations and low-frequency vibrations of gas phase molecules. The high-frequency rotations involve, to a large extent, very light molecules in which the fundamental rotational transition is in the far infrared. So we've learned a lot from this telescope, and I'll only talk about some of the things I've been involved in. So this rather complicated-looking picture is a study mostly of diffuse clouds in the spiral arms of our galaxy. Now, this is not our galaxy. Of course, we're inside our galaxy, so I would have to show you a cartoon. So instead, I've picked another spiral galaxy. And the idea here is that one's going to see clouds in the so-called spiral arms. I'm going to see them in the far infrared in absorption, not in emission, against various lamps. These lamps are not perfect. They tend to be star-forming regions. And in addition to continue in the far infrared, often you see also emission lines to confuse the issue. But this is an example of the center of our galaxy, which is a very good source. Now, in these diffuse clouds, and by the way, diffuse clouds typically are ones you could see through in the visible. Of course, this here concerns the far infrared, not the visible. And typical temperatures, translational temperatures, 50 to 100 Kelvin. Densities lower than what I showed you before. And there's both atomic and molecular hydrogen. And depending on the density, the atomic hydrogen can be greater or at most about the same as the molecular hydrogen. So it's very, very different. And yet, as these objects get studied more and more, we see that there are lots of molecules there. We used to think in the old days there was mostly atoms and a few diatomic molecules. Life has become much, much more complicated. In fact, here is ammonia, 4-atom molecule. And we have a hard time explaining this chemistry. Now, I'm not going to try to do that, unless you want to ask questions about it. I'm going to talk about one thing in the diffuse clouds that puzzled me and others for a few years now, and that is orthopara ratios. Okay. Orthopara ratios in these non-equilibrium plasmas, which are interstellar clouds, could be very, very confusing. We've already heard about H3+. So the orthopara ratio for H2O+, which is a strange ion to begin with, I mean, it's very reactive, but it's still seen, is 4.8, plus or minus 0.2, according to astronomers. Whether we believe them or not, we'll see. So I wanted to talk about that. And then I also want to talk about some strange, warm, dense regions, which actually surround the lamp, the sources. So they're very close to the sources. And they may be even harder to understand than the diffuse clouds that are farther away. This means this is where we're looking. All right. So now to show you a real lamp, okay, this is a relatively close. It's called Orion KL. It's part of a giant molecular cloud with thousands of stars being formed and forming high mass, very bright ones, low mass ones like the sun. And so what you see here has nothing to do with what I'm going to talk about other than the fact that it's a lamp. Now you see an emission spectrum here, and that actually is caused by something actually behind this very bright part of the sky here. It's called a hot core, and it's a star in the act of forming, and actually has many more terrestrial molecules than the cold core. This is another thing that's a little confusing, but not the subject of the talk here. So this is the lamp, and in front of this is also a far infrared continuum, and in front of it there is one of these sources that I want to show you, this hot and dense cloud. So it's not cold and dense, but it's hot and dense. And here's a spectrum looking at some of the molecules. Now, astronomers plot sometimes not against frequency, but against velocity. And it's a little complicated. This is called the local standard of rest. It's similar to what the Earth is doing. So, but in any case, it's a real mess. Ignore all of the emission spectra because that comes from farther inside the cloud. And so the absorption, in particular, we're looking at the negative frequency, the negative velocities here. So this is an outflow source in front of a lamp. So the material is coming right at us. And among the things one sees, the OH plus, H2O plus, the unusual reactive ions that are somehow there. And one doesn't see H3O plus, which is very unusual because any type of discharge with hydrogen and oxygen or water, it is dominated by H3O plus, but there's no really strong evidence for it. So we have to explain why there's lots of OH plus, about twice as much as H2O plus, and much greater than H3O plus in this region. All right, so it's called the Orion outflow source. It goes between 0 and minus 50 kilometers per second towards us. And we're particularly interested in explaining these ions because they shouldn't be there. They react on every collision, as we learned yesterday, with molecular hydrogen, yet they're fairly abundant. So this is what the model here that's being used by my former students is what's called a photon-dominated region. Work started by Alex here. Photon-dominated region is the chemistry is strongly dependent on the radiation field. And as you can see from that picture, it's a rather strong radiation field. So now my student was very ambitious and actually did a time-dependent model in which he worried about when the stars are actually turning on in the Orion Nebula along the line of sight. And the reason for doing this is when you don't have very bright, short-lived stars, that's when a lot of water ice can form. And then when the high octane stars form the O and B stars, and there's a lot of light and heat, then the water evaporates. Okay. Now the conditions which seem to be best for OH plus and H2O plus are 400 Kelvin in the gas, lower temperature in the dust. And what this leads to is very strange, dense cloud. The electron abundance is something like what typically is in diffuse clouds, and there's a lot of atomic hydrogen. There are also lots of X-rays here, so it's a very violent region. So here's the extended chemistry. You saw actually from here to here yesterday, showing, for example, how water and OH are made by an ion molecule chain of reactions. The idea being that cosmic rays ionize molecular hydrogen, which has been formed on grayed surfaces, and the reaction leads to H3O plus, reaction with oxygen leads to this OH plus, and in a typical cold dense cloud, the OH plus is immediately destroyed by molecular hydrogen to H2O plus. The H2O plus is immediately destroyed to give you H3O plus, which is fairly abundant because the electron abundance is not very high in a cold, dense cloud, something like 1 part 10 to the 7th. Okay. All right. So, but what happens to change things? Well, first of all, there are a lot of photons. So one actually has to worry about photodissociation of ions. So H3O plus, any H3O plus that's made, we don't see it. One reason is the high abundance of electrons. Another reason is photodissociation. This reaction has actually been calculated. There's theoretical evidence. Anyway, this one is just a bit of a guess. The point is this leads to H2O plus photodissociated to OH plus. So in other words, without going into this in great detail, the difference here is that there's a lot of radiation, and you really have to take it into account. Okay? And in addition, you have a high temperature because of it. It's a very, very different system. So it's a sort of a violent system. And maybe this is right, although the alternative is to consider shock waves, which we haven't done. All right, so here's an example. This is what's called the column density. So this is the theory versus observation. So you're looking at a column moving towards you, okay? And it's heterogeneous, which is why you're not just plotting a concentration. And this is versus time, and this is an era in which these OB stars have turned on. Okay, so there's a lot of radiation. The horizontal lines are the observed values for OH plus red, H2O plus blue, and for H3O plus, it's only an upper limit. Okay. All right. And if you look carefully at the plots here, there's sort of a reasonable, without not perfect agreement. This is astronomy, which is often an order of magnitude science, and so something like 10 to the 5th or 10 to the 6th years in the modern era seems to come close to it. But of course, if you really want to see if this is right, one has to make predictions of other species and go looking for them. Okay. So it's tentative. All right. The next one, another tentative orthopower problem as regards H2O plus, okay, which is supposed to be 4.8 rather than 3. Now, one does have to remember that in the normal terrestrial laboratory, unless you have a plasma, orthopower ratio seems simple. You typically get 3 to 1. If you have a plasma and you can exchange protons, then you can get thermal equilibrium, which would only be 3 to 1 at high temperature. Now, H2O plus is a little more complicated than that for a number of reasons. First of all, it's in this doublet B1 state, so the electronic wave function is asymmetric. So the ortho and para switch. So the lowest state, this is the asymmetric top levels. The lowest states, there's fine structure and hyperfine structure to make life complicated, but the lowest one is ortho, and the next one up is para. And this is a diffuse cloud we're looking at now. It's no longer the dense clouds, it's the diffuse clouds along the line of sight. And so the chances are we could just worry about the lowest ortho and the lowest para state. There isn't enough of a density to really maintain a collisional excitation. All right, so 30 Kelvin, this is not a temperature. Astronomers use Kelvin for energy, so it means that the first para state is about 50 wave numbers above the ortho state. And all right, if things are in equilibrium, it goes to 0 Kelvin. Then the ortho to para ratio goes to infinity because everything is down here. At a higher temperature, at an infinite temperature, it would go to 3 in the normal course of events. But given the low density here, chances are it's still mostly in the lowest rotational ortho and para stacks. So I would say 1 rather than 3. So anyway, 4.8 at least is between 1 and infinity. So, all right. No, it's pretty bad actually. So here's you have to consider 3 types of processes. First, the formation. Second, equilibration, which may or may not go to completion, and third, destruction. Okay, so that's the simplest way of looking at it. Now, here's what we think is the formation reaction, which we've now seen several times. So OH plus reacting rapidly with H2 to form now, we divide it up between para and ortho, and we have to know what is the fraction. Now, believe it or not, there are theories for this, and we use the version of Oka, which uses just angular momentum theory, and that gives you the fraction of para and fraction of ortho. Unfortunately, there's a problem. It really depends on the mechanism, whether it goes via complex, which is what we normally assume, or whether it's a long-range hopping mechanism. So the angular momentum is different. And then we also have to know the ortho-para ratio for H2, which indeed is measured in diffuse clouds, so that we know, and that's pretty much about 1 to 1. All right, if the H2O plus formed undergoes rapid equilibration, it's not really important how it formed, because the equilibration erases its memory. The only possibility here would be with atomic hydrogen, because it reacts with molecular hydrogen. So if atomic hydrogen could exchange efficiently, you could reach an equilibrium. And if that's very rapid compared with destruction, here's the formula for the equilibration of the two lowest, the lowest para and the lowest ortho state. These are the rough degeneracies. It's actually not quite degenerate because of fine and hyperfine structure, but these G's are both 6. And people know they're not going to get the right answer, so they call this a spin temperature, because it's not going to be the same as the translational temperature. So if you assume you know this 4.8 leads to 20 Kelvin as a temperature. What that means, I think, has no meaning at all, because it's certainly not that it's a temperature involving two levels. It's not equal to the translational temperature of diffuse clouds, which are 50 to 100 Kelvin. If, on the other hand, we say, let's put in 50 to 100 Kelvin, assuming things are really at equilibrium, then we get an ortho-para ratio of 1.4 to 1.8, which is not 4.8. So this fails. All right. So what about the opposite extreme? The opposite extreme is that atomic hydrogen, for some reason, is very poor at reacting and exchanging ortho and para. How about then destruction, such as dissociative recombination, is the more rapid process? If that's true, then we have to worry about whether it's independent of an ortho or para state. And maybe this could be discussed, but I've assumed, since this is this direct mechanism, that it is independent pretty much of whether H2O plus is ortho or para, which means that the only thing that's important here is the formation. So we have to go back to the algebra from Oka's paper, and what you get at steady state is that the ortho to para ratio is equal to this. This is the ortho to para ratio of molecular hydrogen. This means starting with para hydrogen, you get ortho H2O plus. Starting with ortho hydrogen, you get ortho H2O plus. This sorts of thing comes right from his paper. And assuming that the ortho to para ratio is 1, which it is pretty much in the nearby diffuse clouds that was studied many years ago, we get the following result. We get 2 to 1 if it's formed by complex, and 3 to 1 if it's formed by hopping. We don't get 4.8 to 1. Somehow we need something that helps us go down the ladder from the lowest para state to the lowest ortho state. So thinking of strange and out-of-the-way types of calculations, we even worried about radiative emission, because remember, this is a radical, and they're coupling. So I, in a sense, is not a perfect quantum number, and you might indeed have some sort of radiative, off-diagonal radiative magnetic dipole transition. This was calculated by Tanaka, who, along with Oka, are collaborators in this so far unsuccessful project. Anyway, we get a rate which is, this looks very small. This is astronomy, remember. So, if it goes with an Einstein A coefficient of 10 to the minus 2 per year, that might be reasonable, but it isn't. It has to be about 2 orders of magnitude faster. If it were 2 orders of magnitude faster, it would compete with the various collision processes. And we might be able to. Anyway, it doesn't. And the last thought was maybe there's a very strong radiation field. As the ortho and para H2O plus, as they're formed, the next thing that happens is they're going to cascade down. And there were some calculations between nearly degenerate excited ortho and para levels in which the rate was actually a little faster for spontaneous, for stimulated emission. Anyway, it doesn't work. It's still too slow. So we don't know. when this happens, we think probably that it's time for the observers to go back and look at the data, because factors of 2 in astronomy are often, mistakes are often found. And the person who actually looked at, who measured the para H2O plus thinks there may indeed be a problem with it. So there's a lot of time spent on it. Anyway. Okay, perhaps most controversial and confusing of all is having to do, now somewhat older than the Herschel data, the idea of the negative ions, observations of negative ions in space. Now there are, let's say, I wouldn't say quite a few, but a reasonable number of these negative ions. They tend to be electrons attached to radicals with about the largest electron affinities possible. So typically about often close to 4 electron volts. So you have these electrons attached, and different sources have different numbers. And with this IRC 10216, they're the most prolific. That's actually a circumstellar cloud rather than interstellar cloud. So, right, the other thing that's very important about them is that typically the bigger the ion, assuming the electron affinity stays the same, the more abundant it is compared with the neutral, so whether it's a precursor or not. So C8H minus over C8H, the observation is something over 10% is negative ions. So they're very prolific. Okay. All right. So long ago, right after I'd been a postdoc with Carl Leuenberger at the University of Colorado, and he wondered why negative ions had not been seen in the interstellar medium. To try to cook up a theory, I did try to cook up a theory. And the theory used this rather strange radiative attachment process, which is certainly well known for atoms. But in any case, this is now supposed to be for molecules. And I used a very, very simple theory for it, a statistical theory I'll show you, and estimated something like for large neutrals that have high electron affinities, it might be that you could get 1% of some species A in the form of A minus, which appears to actually to have been low. And I didn't just invent this, really, because at the time there were people claiming that they'd seen this in the laboratory, typically with ICR experiments. So these are very low density. It's not quite clear that it's really a two-body process. They may have seen a three-body process as well. Anyway, but the claim was that these could be very rapid up to the capture rate, which for electrons is quite high. All right. So the simple theory used in 1981 was the following, and now I just, as an example, using one class of negative ions now seen in space, mostly because of the work of Mike McCarthy, Pat Thaddeus. Anyway, the basic idea is forming a complex. I mean, this is what chemists do sort of all the time, RRKM type theories. So it forms a complex, and the complex forgets everything but its energy, and I also conserved angular momentum. So then it's called a phase space theory. And then the idea was you had to at least know, you had to know the vibration and rotational energy levels. You had to calculate the Einstein A coefficients that were involved. So compared with the detailed theories that people have been discussing here, you're experts, I'm not, what this does do is it includes a density of vibrational states. So we're not just assuming a resonance into one state, or if we are then assuming a subsequent energy transfer into all of the energetically allowed vibrational states. And that, of course, gives you a complex lifetime, which increases with either the size or the electron affinity, or both. All right. Okay, so the last talk of the conference will be Slava saying that he gets much lower results using a more detailed theory. So anyway, whoops. What happened here? Okay. All right. So attachment rates. There's a weak temperature dependence, and so the C28. This would mean the formation rate of C2H minus, which is very slow, at least by these standards, and it gets quickly much higher. So this, as it turns out, is obviously wrong. It's too high, but for simulations, these very large results for C6H minus and C8H minus seem to fit the data. So if they're not right, we do have a bit of a problem. All right. Now, the key thing, by the way, is once some negative ions are made by this sort of primary mechanism, then others could be made by exothermic ion molecule reactions. So, for example, Cn minus, it cannot be made by, in this very simple statistical mechanism of radiative attachment. Instead, this reaction, these reactions were seen in the laboratory. Cn minus are also could be made by radiative attachment, so it's claimed. And so then this reaction would give you Cn minus. So then H minus is actually in stars, and so perhaps in stellar atmospheres, these types of reactions would also work. The key point is it's very hard for us to form anything small by the radiative attachment mechanism. So. All right. So here are some results for ratios. So what's listed here is from a model which is not mine. I mean, the only thing that was mine here was the calculation of the rate coefficients. But this is the model result, and this is what's observed. So I put it in two separate classes. So here are the CNH species. By the way, the odd ones just haven't been studied, so we wouldn't know where to look for them, and they're not even linear. But in any case, here the model, this is again, it's not very big, so even with a large electron affinity, and with the electron attachment is very slow, and even the forming it from bigger species by exothermic ion molecule reactions doesn't work much either. So anyway, so that's reasonable agreement. I mean, C4, this is the biggest disagreement. It's a 2 order of magnitude disagreement in which obviously the radiative attachment rate is much too large. Okay. On the other hand, when you get up to these bigger ones, then there's, again, by astronomical standards, very reasonable agreement. All right. Now, this other family, again, Cn minus, this is not formed by radiative attachment, but it's reasonable agreement, and again, factors of a few for these bigger species. And the idea, and then is the bigger the species, until it saturates, the higher the ratio. Saturates something like about 10%. All right. So if we're going to give up on radiative attachment, then we have to do something that will still give us this trend. And I'm not sure what the answer is. I mean, one possibility that works for C6H minus is what you're talking about, dissociative attachment. The problem with most of these dissociative attachments, as you know, they're endothermic, and we're talking about a 10 Kelvin region here, so that may be a problem. So, for example, if you have electrons hitting this triacetylene, forget about this complex here. But the point is, it's quite endothermic. Of course, we don't know the resonance structure anyway. On the other hand, what we do have to remember is we have a lot of strange... Can you give us the conversion rate, kilojoule per mole to, say, Kelvin? Yes, I can. Let's have to do this. So this is about 40 kilocalories, and each kilocalorie per mole is 500 Kelvin, if you really want Kelvin. Maybe you want electron volts, right? It's about 2 electron volts, right? What? I didn't do this. This is a quantum chemist. I'm happy with electron volts. In any case, but we have strange isomers. So here we have this cumulene carbene form, and actually it's downhill. So even if you have thermal electrons, I mean, I'm not sure what the mechanism would be, but even if you have thermal electrons at 10 Kelvin, it's possible that it works. And if it does go at, say, the collision limit, it is about equally efficient to the radiative attachment, okay, according to a Japanese group. Do we have enough of these strange isomers to make out? Maybe we do. I mean, we don't. I mean, we have to try to consider it. In a more general case, though, if we're worrying about these endothermic reactions, we are going to have to worry about whether we have any non-thermal electrons, which is something I don't think we've thought about for some time. Maybe, Alex, you could correct me on that. But, you know, if all discharges, besides having thermal electrons, have a high-energy non-thermal tail, and the chances are it's the same in space. Okay? And one possibility to check, I mean, I'm not sure about, again, the resonance structure, this particular reaction is weakly endothermic. And so it might be interesting to try to look for this NH2 minus once we know its rotational spectrum. Yeah. Okay. Okay, but even if we try to replace the radiative attachment with dissociative attachment, it's not clear what mechanism is going to give us this business that we want larger ions rather than smaller ones. So maybe we could discuss that. Okay, and the last thing, okay, is if one believes radiative attachment, why not radiative recombination replacing dissociative recombination? C60 has now been detected in the infrared in regions of the interstellar medium. There's a recent claim that C60 plus has also been detected. We have suggested ion molecule syntheses up to this, and then there's a roadblock actually to making that. And one possibility might be, if you have a big enough system, that it is a heat bath and electrons can attach, perhaps. And so, as you see, I've given you some examples of what happens often in astrochemistry. When we think we understand things, often we find we don't as new data come in, or old data get reinterpreted. All right, let me just end by giving these standard acknowledgments, and thank you for your attention.
Question, Chris.
Not sure I understood why you think H3O plus is so small, smaller than expected. Did you address that?
Yeah, first of all, there are a lot of electrons, so it's destroyed more quickly. The chain of reactions with molecular hydrogen from OH plus is slowed down by the fact that there's atomic as well as molecular hydrogen, and dissociative recombination is now competing for destruction of OH plus and H2O plus. But even so, if you took, I didn't dwell on the slide, the model does make too much H3O plus. It predicts more than has been detected. And some people believe it has been, that really there is some stronger evidence that it has been detected weakly, that my statement that it wasn't detected may not be exactly right.
So you had some reactions with H minus.
Yes, that was for a stellar source, yeah.
Okay. So
yeah.
but the electron's not bound strongly to the hydrogen. So how is the H minus made?
The H minus is made. Let's see. There's radiative attachment in the early universe. There's three-body attachment in the atmosphere of stars. For example, in high temperature atmosphere in the sun, right, H minus is very important in the opacity of the sun. One reason why you can't look through. So that is I guess at densities of near pressures near 1 atmosphere. So it's probably a three-body process, I guess. Yeah, it's only 3/4 of a volt electron affinity.
Anything else? Okay, thank you, speakers.
Transfer this in.
Oops. Don't want to steal this.
No, this is the we had escape. Try to escape. I have no idea. It seems frozen. What's this do? Does this work? No, everything is frozen. You may hit those two buttons plus escape, and yeah, and then you can quit it and restart it. Yeah. Even that doesn't work?
That doesn't work.
I've never heard of this.
Macs are never supposed to freeze.
Max don't freeze. Yeah, but I've never seen this.
Well, that's why we just restart.
No.
let's disconnect this and do this. Maybe that's screwing things up. Yeah. See that? Now, did that work? Oh, this is bad. This is really frozen and it won't, where's Bob? Did that work? It's starting?
No, it's not starting.
Yeah, there it goes.
What happened to me before on the water?
Never had?
No.
I'd make sure it's all working properly before you connect the,
Yeah, exactly. I'll make sure it's, we checked it before, it was fine.
okay. Should be okay. Now let's go to this one. Now you can plug it in. If it ever works. There you go. That should
No, it's-
work. There it is. Okay.
All right, there we go. I don't have it. Okay. Is it on? Is it on?
Yeah.
Eric, do you have the pointer? Oh. Oh, this is it here? All right, well, thank you very much. Sorry for that technical difficulty, but it's a pleasure to be here this morning, and I want to start by thanking the organizers as well very much for the invitation to tell you a little bit about the work that we've done in terms of the laboratory and astronomical spectroscopy of molecular ions. And the work in the laboratory is mostly done here at the Center for Astrophysics, and as you'll see, most of the astronomical work has been done in collaboration with astronomers here and abroad. And it's important to emphasize this is actually a fairly new field, a field that's only about 5 years old, in terms of detections of negatively charged molecules in the interstellar medium. So I'd like to kind of go through, at least briefly, and give you a kind of historical perspective of how we got to the point that we are in terms of laboratory spectroscopy and ultimately the astronomical spectroscopy, which has advanced quite quickly in the past few years. So as Eric already alluded to, in fact, in 1939, before we knew anything about molecular astrophysics, before molecules, even diatomic molecules, were detected in space, it was shown by Rupert Wilt in 1939 that H- is the source of optical opacity in our sun and similar stars. So that is, if you look at the sun, and I do not recommend you do that regularly, that is in fact the species which gives rise to the opacity. Shortly after that realization, in the early 1940s, CH, CH+, and CN were detected optically, and then there was a long hiatus, and then molecules were detected in the late 1970s, or late 1960s and early 1970s, and we have this tremendous amount of activity of quite extensive laboratory spectroscopy and astronomical spectroscopy with detections of about 150 molecules as of about 2006, and most of those are neutral molecules. We've already heard many of them are exotic and unusual by terrestrial standards. About 10% of them are protonated or positively charged. But no negative molecular ions were detected in space during that long period of time. It's important also to point out that, in fact, negative molecular ions were predicted theoretically by a number of groups, by, in fact, a number of people, several people who are here, in fact, to be constituents of the interstellar gas. And under the right conditions, they could be made in a wide variety of astronomical sources, and they, in fact, could be quite abundant. People like Eric and Alex, in fact, predicted this many years ago. In terms of the laboratory spectroscopy, in fact, there is a tremendous amount of work done on negatively charged species, right? I mean, this is a very important thermodynamic quantity for physical organic chemists. You determine the electron affinity of molecules, and there's been recent tabulations, and there's well over 1,000 of these that have now been determined. The electron affinity has been determined, but that's at very low spectral resolution. So what we want to do, obviously, is to, from the astronomical perspective, have very precise laboratory rest frequencies, often in the radio band, because this is the transitions which are most intense in space, and so that astronomical searches can be done very efficiently. So if you look, in fact, of these 1,000 or plus molecules that have been detected in the laboratory, what fraction of them are known at a very high spectral resolution? In fact, only 2 have, up till 2007, had been detected in the radio band, and their rotational spectrum very precisely determined, and that is OH minus and SH minus. There were a few more which were detected in the infrared, and the rotational structure was resolved, and therefore the rotational constant was derived fairly accurately, not quite to the accuracy which we'd like, that is to a fraction of a kilometer per second in terms of equivalent radial velocity. That is, we want to know the line frequency to a fraction of a line width. And this was mostly worked by the Sakeley group, things like NCO minus, NCS minus, and a few others. In addition, there was rotationally resolved electronic spectroscopy done by the Boulder group and by John Meyer as well on a few simple species as well, which had some rotational resolution and therefore derived, again, an estimate of the rotational constant. In terms of publishing, or at least searches in space, there probably are many more, but the only one that we're aware of that was published was an unsuccessful search for small negative molecular ions, based, again, on either calculations or on infrared data. And that was done in 1995. And the idea there was, again, to follow the history of detections of molecules in space, small molecules that are typically detected, and then ultimately larger ones as well. So you built up from small chains to larger chains. Which brings us to, in fact, a very nice paper, again, more than 15 years old now, by Ken Kawaguchi and his coworkers, in which they looked at this very rich source, IRC plus N216, which you've already heard a little bit about, which is a central star CW Leo. You can see it kind of right here. It's one of its last stages of the cellular evolution, what they call the AGB, or high mass loss phase. So it's surrounded by a thick circumstellar shell of gas and dust, and it's sufficiently close to us, in fact, with powerful interferometers, which I'll show you a little bit more about in the talk. You can, in fact, spatially resolve and do time-dependent chemistry and look at the distribution of molecules as a function of time from the central star. And you see this, a variety of maps have been made for these fairly exotic species like magnesium NC, CCS, and some of these carbon chain molecules as well. Most of them are in this outer circumstellar shell of this evolved carbon star. What they did is a spectral line search. They simply looked at over a range of frequencies, detected a number of lines, and tried to assign as many of them as they could to known species, whether they be in the ground state, the isotopic species, or vibrationally excited state. And in fact, we know this is an extremely rich source, about 50 or so molecules. About a third of all molecules have been found in this source. And they were very successful in detecting many, many molecules. However, there was one, actually two, but one more interesting series was found for which they could not assign to any known species, any isotopic species or vibrationally excited state. And that two of the lines in the survey are shown here. And it's important to emphasize that the structure of these lines is not due to the underlying electronic structure of the molecule, but rather the fact that this is a circumstellar shell and there's gas coming towards you and away from you. And that's what this double peak line shape indicates, that the molecule is formed in this circumstellar shell. And there are, in fact, a very simple relation between the frequencies of these lines. They're ratios of integers. So, this is kind of freshman quantum mechanics here. From this simple relation, you would conclude that the ground state is a closed shell singlet sigma molecule. And from the rotational constant you derive, you get a B value of 1,377 megacycles, which is within 1% of this very well-known radical in the source, C6H. So an obvious candidate, based on those two facts alone, is C6H minus, right? So you have an open shell radical, you add an electron, and you form the closed shell ground state. And it seemed, however, that this explanation was dubious in the extreme, in the sense that history really does repeat itself. It's remarkable how often that happens. And it parallels really the early history of interstellar molecules and the objections as to why molecules themselves could exist. right? First of all, the absence of evidence becomes potentially the evidence for absence. No molecular ions have been detected over a period of 30 or 40 years. Therefore, and there have been searches for these small ones, so why in the world would you have a negative molecular ion? Second, it seemed very unlikely that the first negative molecular ion that would be found would be such a big molecule, at least by interstellar molecule standards. It was larger than most of the neutral molecules and all the cations. Another parenthetical point is that people had often thought that the fractional ionization in the source was very low because HCl+, which uses a measure of the fractional ionization, is in fact very, very weak. So people said it's not even a very weakly ionized source. And third, of course, is this well-known explanation for all phenomena, right? We don't know how molecules are made, but we know how they're destroyed. We simply expose them to starlight, they fall apart. So if you're not careful, that's a rate equation, right? I know how they're formed, I don't know how they're formed, but I know how they're destroyed, therefore the steady state population is 0, right? And that's exactly what was used in the early days as to why molecules themselves couldn't exist. And then finally, since this is a fairly exotic explanation, at least on the surface, you really need laboratory data to be absolutely certain for this identification. So we had really struggled with this series and tried to explain it by different means and more exotic explanations. And the real advance was not any laboratory work, but actually detection of this series in a second astronomical source, the source TMC1. Again, a very rich source for molecules, but a much different source, a cold molecular cloud, not a circumstellar shell. And we were actually looking for something else, but we knew, in fact, that the lines, if they occurred, would be within the band of the search. And there are two fairly weak lines that we found with a modest amount of integration time. And these are exactly the frequency you expect from the higher frequency IRC plus N216 data. What's important is that it really rules out a metal-bearing molecule. As I've already indicated, there's things like magnesium and calcium. Silicon molecules are found in IRC. Very few, if any, of those are known in this source. Secondly, this is a cold molecular cloud with a very low rotational temperature. So you now know you're looking at low J transitions, and these are razor-sharp lines, and there's no structure to these. So you can rule out that there's some accidental collapse of structure of some kind, and you can be certain it's really a closed shell sigma ground state. And in some general sense, it tells you now we found this two series of lines, the same carrier in two different sources. So it's arguably a more fundamental molecule. So on the basis of this second astronomical detection, we were confident, I should say, that the carrier had to be C6H-, not because we ever embraced C6H-, simply because there were no other candidates left. All right, so I won't go into detail here, but we use a technique, several techniques in our laboratory. The most powerful, one of the most powerful methods we and other people use is for a transform microwave spectroscopy, and the idea is you simply couple a supersonic molecular beam to a discharge source, and this is a very efficient way to make larger molecules, radicals, carbines, highly energetic isomers, protonated molecules, and ultimately negative molecular ions as well. So they break apart, reform, and a variety of species are produced in this cold adiabatic expansion. The temperature is a few degrees Kelvin, and that's well coupled to the frequency range of this device, which is in the centimeter band, typically 10 or 20 gigahertz. And then we apply a pulse of radiation to listen for this echo. And just like in the IRC case, our laboratory lines are doubled because of a Doppler effect. We have an axis of expansion along the cavity axis. So it's a very high sensitivity, high resolution way to detect the rotational spectra of unstable molecules. And what we're able to do is to detect with this device, as well as a long path DC glow spectrometer, in fact, lines in the laboratory with both of those spectrometers with two different hydrocarbon gases that are exact frequency agreement with the astronomical lines. All right, now the beauty of this, again, freshman chemistry, there's two parameters to describe the spectrum of this molecule. It's a classic rigid rotor. You have a rotational constant and the very small correction for the fact that it's not infinitely rigid. Right, and you can see from here the laboratory spectra, obviously these are very sharp lines, so there is perfect agreement between the laboratory and astronomical. The astronomical is somewhat more uncertain because the lines in IRC are somewhat broader. And this is an indication that between the laboratory and astronomical, and the lines that we derive are with half a channel width in this source, TMC1. So there's no doubt we've detected in the laboratory the carrier that's giving rise to the lines in TMC1 and IRC plus N216. The only question becomes, what is the carrier, right? And it's fairly obvious what the carrier is. We use hydrocarbons, so it contains carbon and hydrogen. We know that the lines are linearly related, therefore they have to be, all the heavy atom weight has to be along the same axis, the A rotational axis. We know it has to have 6 and only 6 carbon atoms because more or less the rotational constant is off by tens of percent. And we know it contains hydrogen specifically because we can replace hydrogen with deuterium, and the line disappears and another line appears, and that shift is characteristic of hydrogen at the end of the chain. So then we're left simply with the neutral and the both positive or negatively charged variant. Obviously the radical is well known, and C6H plus has a triplet sigma ground state, not in agreement with what we observe. So by default, it has to be C6H minus. So arguably, we go from not knowing what the carrier is in a matter of a few weeks to the fact that now you can argue that C6H is arguably one of the most securely identified, best identified or securely identified astronomical molecules. We have very good laboratory spectroscopy to support the astronomical work. Okay, so an obvious question then to ask is, well, why C6H minus? What properties does it have that make it, in this case, detected in these two sources? And there are basically 4 factors. Number one is, it's been argued that you might expect a larger molecule like this to be formed by radiative attachment. Therefore, if true, then you need the radical to be present. In both sources, C6H radicals is abundant. Second is a point which is a departure from kind of traditional neutral and cation chemistry where we build up from small molecules to large molecules, and that is size confers stability. Apparently, C6H minus is large enough whereby this attachment of electron does not destroy the molecule, and that process becomes at least somewhat efficient. Third is, in some sense, C6H minus is not very, well, it's a highly stable anion. It's got a binding energy that's been measured, and it's nearly 4 electron volts. Right? That is a very large number. And fourth is, I'll show you in a moment, is this idea of spectral simplification that we get upon electron attachment, whereby the lines of the anion are 10 times more conspicuous if both the neutral and the anion are present at the same level of abundance. So this is just a simple cartoon here showing you, of course, the basic idea that if it's electron attachment, you add this electron, you get a acetylenic-like structure. It's basically triacetylene, where you're moving this proton out to infinity, and this electron pair occupies this very tightly bound sigma-type orbital on the carbon with S character. And again, the electron affinity is extremely high compared to most molecules which have been measured. Second is this idea of spectral compression. So this is actually a spectrum in IRC plus 10216 for C6H for a single rotational transition. And it has, again, this total of 8 lines, counting the Doppler from the source, 2 of which, or 4 of which arise from the fact that it's the double sigma inverted ground state with the double pi 3 halves, lower in energy, and it's warm enough, in fact, that you also see transitions from the double pi 1 half, and you have hyperfine structure from the hydrogen. So you have 8 features. However, when you add this electron, what happens is all this structure, nearly blinded myself here, all this structure collapses into a single feature here, right? So this is the same line of C6H minus. And again, you have this very simple structure here. So all the structure collapses down here. In addition, you take a polar molecule and you make it even more polar upon electron attachment. So the calculated dipole moment is about 5.6 for the radical, and it's about 8 dBi for the anion. Detection sensitivity in space goes as a square of the dipole moment, so that's another factor of 2, meaning roughly about a factor of 10 enhancement upon electron attachment, which is obviously helps very much detection in space and in the laboratory as well. Eric kind of touched upon this topic, but electron radiative attachment calculations have been done, assuming kind of a 2-step process where we add in his calculation, where we form the temporary negative ion, and then we ask the question, what is the probability that it will form the anion at ground state, or will it simply auto-detach the electron? And what he finds is, in fact, as you increase the chain length, owing arguably to some kind of generalized density of states argument, the probability that it will detach the electron goes down precipitously, and the overall rate of electron attachment rises to a fairly constant level after of order of 5 or 6 or so, or 4 carbon atoms. So this process of electron attachment in his calculations seems to be relatively high once you reach some modest size chain length. So what are the implications from this discovery? What should we do in the laboratory? And for that matter, what should we do in space? Well, what we should do is we should obviously try to detect other molecules or other ions that have these same basic properties, right? We should, in fact, try to observe anions for which the radical is well known in sources. We should, hopefully, when we add the electron, we'll get a closed shell sigma ground state. We'd like the dipole moment not ideally to go up a lot, if not go down not too much, and we want to focus on those with high electron affinities. All right, and so in fact, these are the properties of these shorter and longer members in the series, as well as CN and C3N. And you see electron affinities are all quite high. The dipole moments of the anions are extremely large. Notice C8H minus is about calculated to be 12 dBi. And they're all closed shell sigma ground states. I should point out C6H minus among these series is actually the least favorable case with respect to this spectral compression. If you take C4H, for example, it's a doublet sigma ground state, and it's a doublet singlet sigma upon electron attachment. So the ratio now, you go from 0.9 to 6 dBi squared is a huge enhancement. So C6H is actually the least favorable case where you only get a factor of 10. And so what we've done now in the laboratory is, in fact, measure at high spectral resolution the rotational spectrum of all of these carbon chain anions, from C2H to C8H, as well as Cn minus and C3N minus. And not a carbon chain, but a related species, we found now the rotational spectrum of NCO minus as well. And I won't go into detail here, but we do the same kind of tests in terms of harmonicity, elemental composition, isotopic shift. In many cases, we can directly determine the ionization state by looking at the ion drift of these species. So these are all secure and now have all the data we need to start looking for them in astronomical sources. And although it was, as often the case, because astronomical time is competitively granted, the laboratory spectroscopy proceeded more quickly, and now the astronomical spectroscopy is really caught on. So what I'm happy to report is the only one that's not been detected in space of the carbon chain anions is C2H minus, and we believe that in fact C5N minus has now been probably found in IRC plus 10^16, though we don't have laboratory data to absolutely confirm that. As I'll show you, and as Eric has alluded to, in fact, the abundances are fairly constant and in some cases very high, specifically for C8H minus, where about 35, of order a third of the molecules are negatively charged in this, for C8H. And the recent detection of Cn minus in IRC in fact suggests it's present about 0.2% relative to the radical. That is not consistent with radiative attachment and suggests a formation route involving carbon chain anions and the reactions with nitrogen, which has been studied by the Beerbaum group. So again, this is a summary that Eric showed, in which we've now plotted the ratios of the anion to neutral in both TMC1 and IRC plus 10^16. And you see for the longer chain molecules, the agreement between the calculations and observations is fairly good, within a factor of a few in most cases. But when we go to the shorter chains, C4H minus in particular, the ratio is far from that calculated. The observation is far from that calculated. And that not shown here is, of course, the case of Cn minus as well. And so that's telling us, obviously, there are formation and destruction mechanisms that we certainly do not fully understand, and reaction rates that we perhaps need to measure. So what we've been able to do, and with others, is now, in fact, ask the question, are these two sources special? Or can we detect negatively charged carbon chain species in other sources? And the answer is, in fact, they have been found in other sources. We found them in at least 8 sources already. Other people have, mostly in dark molecular clouds. And the ratio is typically kind of 1 to 5%. And so with better sensitivity, we think, in fact, C6H minus as a surrogate for negatively charged species, we can find them in many sources. Okay, that they're probably widely distributed at this level or comparable levels. And what we did a wider search looking at a number of sources, and we found an empirical correlation between the negative ion, the radical, associated radical, and the shorter members, suggesting there's probably this sequential formation route from production of C4H to C6H, and then perhaps electron attachment to form the negative ion. And this is just one example in the source Lupus 1a, where you see again by Sakai and others detection of C6H minus. And we can also, of course, learn about the fractional ionization in an analogous way to what is used for positively charged species to derive the fractional ionization arguably more directly, because we're looking at the negative charge. And the value that we derive in these sources is actually fairly similar to that derived from HCl+. All right, so we can also then, ions are now being incorporated into models. Eric has done this, in fact, and this is simple schematic is shown here. But the point is that negatively charged molecules, carbon chains, provide us with new formation but also destruction routes. And this is just one example where they calculate the production of various acetylenic-like chains with and without anions, and it appears as if at least negatively charged molecules are a way in which we can form with greater abundance still larger molecules, arguably because the negatively charged species is a more gentle collision partner than our electrons. All right, so I think that work is continuing and moving forward in terms of the role that anions now play in this more complex chemistry. As we alluded to, we can determine things like the rate of radiative attachment, and we can infer the ratio or the fractional ionization, because the ratio of the anion to neutral has been shown by several people is a very simple relationship related to the rates of destruction, in this case with atomic hydrogen predominantly, and radiative attachment. And so if you can get estimates of 3 of the 4 factors, you can infer the rate of radiative attachment in these sources, assuming steady state. And the values that were derived from the astronomical observations are shown here. So the last part of the talk, let me just briefly show you some fairly recent astronomical work in which we're now trying to understand more carefully the distribution of the negatively charged molecule with respect to its neutral counterpart in this source IRC plus inter-16. Again, these are interferometric maps with the plateau de Beer, which is now being upgraded both in terms of the number of elements as well as the baseline. But this is a nice picture in the winter shown here. And there again, there are some molecules which are only formed in this central star or near the central star, while others are formed in this outer circumstellar shell. And again, this is time-dependent chemistry, whereby this is about equivalent in time to about 1,500 years. So our collaborators in France and Spain have looked carefully and developed various models to try to understand how these carbon chain anions, where their abundance peaks, and using, in this case, a smoothly decreasing density distribution. But you see most of them are thought to peak at this typical kind of circumstellar distance, which I've already indicated here. C2H minus is only thought, if it's formed, to form in this very close to this central star because of the perhaps reactions with H minus. This is a calculation for CN, where CN is peaking, and then where we thought CN minus was going to be peak, and shown here is where we believe, based on the data, it actually is peaking. So it's peaking much closer into the central star than originally expected, and it's closer in than the radical. So this is yet another picture as well, simulation in the source IRC plus inter-16, where in this case, this concentrate on the uppermost plot for the moment. You see the C6H radical is peaking at this characteristic distance, and the negative ion is slightly farther out, again because of radiative attachment. So it should be formed slightly farther out compared to the radical if this simulation and modeling is correct. And so what we've been able to do, the royal we in this case, is in fact now do a low resolution interferometric map of specifically the anion. So keep in mind, negative ions not found in space until about 5 years ago, and now we're in fact to the point where we can do interferometric mapping looking at the distribution in this source IRC plus inter-16. So if you look here, it's not perhaps so convincing, but this is the distribution of the same transition of C6H radical and C6H minus. And you might argue, in fact, that C6H minus is perhaps slightly closer in than the radical, okay, which is not what you'd expect from this radiative attachment model. And what we've been able to do in fairly recently, in fact, is improve the resolution of these measurements. And in fact, that initial observation seems to have borne out. This again is the peak. This is the distribution looking through a cut of this source IRC plus inter-16. Again, this is where C6H radical peaks, and this is the same distribution of the anion. So the anion is peaking at a slightly smaller radial distance, which is an earlier time than the associated radical. This is, again, another slice through this source. And again, you've seen the same effect here where we've overlaid the peak distribution for the negatively charged species as well. So this is not, perhaps given Eric's recent talk there, perhaps there's another formation route, but certainly doesn't not appear to be consistent with this strictly radiative attachment mechanism. This is now just another display of the spectrum in which we take the average intensity of concentric circles. So the HC5N is shown in red here, so that's these circles here, and its peak intensity is out here, about 15 arc seconds or so. The radical is also shown. It's a little bit hard to see in the spectrum, but it too peaks about 15 or 16 arc seconds. And C6H minus is shown in yellow, and that's peaking now about 12 or 13 arc seconds. So slightly earlier time. And we have different plots here. Again, C5N minus we believe is the carrier of these lines, though it hasn't been identified in laboratory. It has a very similar peak position as does C6H minus, about 12 or so arc seconds in. And again, this is another plot showing the same data here where the peak intensity is shifted by a few arc seconds, so it's earlier time. So this is, I think, again, another illustration of where we can do astronomical spectroscopy, do time-dependent chemistry here, and more carefully look at this issue of the formation of these negatively charged molecules, and perhaps an indication now that what ultimately can be done on this and other systems. So in conclusion, at least from the maps, it appears that C6H minus and C5N minus are at smaller radii, which is earlier time than predicted. I didn't show because the data is not as good and less certain, but the opposite may be true for C4H minus. As I've already indicated, the abundances specifically of C4H minus and CN minus disagree with formation strictly by electron attachment, and the present work provides some constraints on the rate of electron attachment in these sources. So I think I'm almost out of time, but what I hope I've shown you is laboratory and arguably astronomical spectroscopy of negatively charged molecules is flourishing, right? Again, in only a matter of a few years, we have accurate rest frequencies for a number of these carbon chain anions. We see a surprisingly high abundances, specifically of CH minus in the source IRC. The ratio is fairly constant in the sources where we have found in other sources. And we hope in laboratory and ultimately in space to extend the spectroscopy at high spectral resolution to a number of other small hydrocarbon systems and other species as well to, again, explore better the distribution of negatively charged molecules. There's a lot of work to be done ultimately to better understand the reaction rates, electron attachment processes, and other formation routes, as well as to properly account for these anions in chemical models. So I will then just acknowledge a number of people, my colleagues, Pat and Carl, and a number of other postdocs who were involved in the work, as well as a number of senior collaborators abroad who've been very helpful in terms of looking at these molecules in space. So I will end very much, and thank you very much for your attention.
Yes. Oh.
Yeah, so both you and Eric mentioned grains, but mostly in terms of the source for electrons. I'm wondering if...
I don't know if I mentioned grains, but I did.
They were on the...
Oh, okay, maybe I did.
So I guess that's the question is, you know, can the grains be involved in the sequential reaction that builds up your C6H parent molecule?
Well, the formation of the radical itself or the anion? I mean, the normal routes for these hydrocarbons are gas phase reactions involving acetylene. So I don't think you build up from, you know, acetylene and then reactions of C2H very, very rapidly build up these longer carbon chains. So normally grains are not invoked for these hydrogen deficient molecules.
Yeah, so the neutrals, they're bent?
No, these are linear.
The neutrals are
Yeah,
linear.
so these are double sigma type states. So they're
why is there such a big dipole moment change? Now, I realize you have to tell us the origin when you're given the dipole moments of the charged species, but some of these are jumping 5 or 6 divide.
well, in the case of C4H, there are two states, a double sigma and a double pi state. So one state, they differ by a fairly large factor in dipole moment. So it depends which one is ultimately the ground state. So when you go to longer chain lengths, you go from C2H to C4H, those are both doublet sigma ground states with small dipole moments. And then when you go to C6H, C8H, and longer chains, this doublet pi state becomes lower in energy.
Pi should be back, that should be a random element, right?
It is a linear, but there's a lot going on. And there's a very low-lying state, but we can fit them as a doublet pi linear system.
So in the larger ones, the dipole moments are large enough, these will have dipole bound anions. So you would think that at least in the larger ones, the low energy electron would be first dipole bound, and then there'd be this interconversion over into the valence state.
Mm. Yes, no, I don't, I mean...
Given the dipole moment of the C4, that's not big enough. So C6
Correct, yeah,
is
exactly.
really big enough.
Exactly, yeah. You get the kind of typical 2 or so to buy.
Yeah, it's tens of MeV. It's very low. It's very low. But
Yes.
if this could rapidly then interconvert over to the valence state, and there's lots of evidence in
Yeah.
the system, these can be doorways into the valence state.
Yeah, big literature.
Yeah, we had for a long time we had a problem looking at detecting C4H minus, and we thought it perhaps was this mechanism, and we still don't fully understand why. Under some expansion conditions, we get actually very strong lines, and other conditions we get very weak lines. And we thought for a while, in fact, the explanation was it was simply populating the doublet pi state, which has a large dipole moment. But anyhow, it's something we have thought a little bit about, but I in terms of experimentally, we don't have much to say about that at this point.
Yeah, C4H minus has just been detected in PNC1.
I did not know that. Who did that? Were we involved in that, or someone else?
No, it was someone else.
Oh, okay, well, and I presume the ratio. It's well, yeah, I don't know. And interesting, though, interesting.
I think it's very close to that.
I remember this paper, I think, from Petrie for the formation of Cn minus, that was suggesting like the dissociative electric attachment of MgCn, of magnesium Cn. Is it this thing has been rolled out, or it's still?
For the carrier of.
Yeah, dissociative electric attachment of MgCn leads to like Cn minus.
MgCn.
Yeah.
As a carrier for the I'm confused. You're talking whether it's a carrier for B1377 or
I don't know. I just remember this paper from.
there was a. Yeah, I remember that paper, and there was a possible detection of. There's 2 series of lines in IRC plus 216. One is at 1377, and one is at 1395. And 1395 is a doublet state, which I think he may have suggested was this magnesium NC or CN, but which we have shown, in fact, is a low-line vibrationally excited state owing to things like Rayner-Teller effect of C6H radical. So that turns out to be somewhat less interesting. I still think that's a good candidate, but it's not the carrier of the lines that we found.
Now, do you observe, so something like your 6 carbons in a row, but with, say, 2 hydrogens, or 8 carbons in a row and a couple hydrogens?
Those must exist, but we can't observe them by rotational spectroscopy because they don't have a dipole moment.
What about the ions then? You still couldn't see.
No, it'd be nonpolar as well. But I mean, in terms of the carbon chain radicals, we can go up to C14H, for example. We've seen carbon chain radicals that long, and if we can somehow impart a dipole moment, then so there's no doubt that they exist and are produced in our discharge expansion, and perhaps as well as in space, but we can't see them.
What about if you have an anion? A bunch of carbons and they have a nitrogen.
Yeah. So.
Bunch of carbons, nitrogen.
Yes. So those are So there's the cyanopolyions, for example. In the laboratory, we did up to HC19N. So you can really run these carbon chains through quite long lengths. There's the radicals, which you can see. And then you can play other games. You can switch the CN group and make the ISO and all sorts of different things.
And what about molecular ions?
Well, we have CN minus and we have C3N minus.
I mean the plus.
Oh, yeah, we haven't found those yet. That's one thing we'd very much like to detect. For example, C3H plus was detected, or reported to be detected in space quite recently, and that has a closed shell sigma ground state. So that actually has many of the same properties in some sense as the anion in terms of the spectral light compression. C5H plus has the same, but we actually haven't looked for those recently. But there's a question of how to form the cations in that sense. We have no problems forming protonated species, but just to kind of rip an electron off a radical is proven more difficult than add electron to a radical.
You might mention, some of those you just mentioned react with high H2.
Well, yeah, but you don't necessarily in laboratory have to make them with H2 or involving much hydrogen. I'm not bothered by that.
Well, the C3H plus does react slowly with hydrogen.
Well, it's only seen as low density.
Yeah. No, I'm just saying that it doesn't react fast with H2.
C3H plus?
Yeah. According to Gerlich's measurement.
So we should look for them.
All right, why don't we thank our speaker, and we will break for a little over a half hour and resume at 10 to 11.